Hello everyone.
Well,
How are you guys doing today? Sorry about the noise. Next to me, people are talking. I'm doing fine. Thank you, Fatima, for asking. How all of you are doing? Did you guys have a good day, bad day, normal day? Good. My week is going busy. Except for that, yeah, I'm doing okay. Yeah, it's getting colder and colder. That's so weird. Just a few days ago, it was so hot, and then cold, and then hot, and then cold again. So it's really hard to predict our weather. Great, great. Good day, lazy. Wonderful. My day was a little bit productive. I modified chapter 11 lecture again to make it simpler for you guys. So whatever you have on Blackboard, my notes will be a little bit different than the Blackboard one. So in the Blackboard one, I have details about everything, which was kind of confusing. So I decided to make it shorter and simpler. And good thing is that I'm also taking a stat class this semester. So this week, the materials our professor teaching us is the same material I'm teaching you guys. So it's cool. I'm what's the expression? Killing two birds in one stone. Yep, I'm killing two birds with one stone. So I'm also starting from my own class, which is the same materials, which I'm going to teach you today. So I'm going to, every week I have to take a quiz for my class. So once I teach you the materials, I'll get more familiarized with the materials. So it will be easier for me to take the quiz. So I'm kind of happy. We are done with chapter 9, 10, and our exam will be on, let me remind you again. Oops, my pen is not working. Oh man. Okay, so our exam will be 25th of November. And our my plan is to give you the exam based on chapter 9, 10, 11, 12. I am not sure how much you can finish from chapter 12, but whatever you can finish, the exam will be up to the point. Okay, and after the exam, we are going to do whatever we couldn't do from chapter 12 and chapter 5, and then we are going to do review for final. And if we are done early with everything, then maybe we can have our final exam on the last day of class. I want to do it on the last day of class because then you don't have to come again to take the final. So our last day of class is 12. Yeah. And for the final exam, you're allowed to have two-sided cheat sheet. And in this exam, just like the exam one, you can use one-sided cheat sheet. Okay. Any question, comments, concern, complaint, anything before we start? Nothing? Okay. So chapter 11, we are going to work with two populations or two types of treatments. So in chapter 9 and 10, we worked with one population, and from that population, we worked with one sample. Now, since we are working with two populations, so we have two scenarios. Either the population you're working with, they're independent of one another, or one population depends on another population. So two scenarios we have. If we have independent populations to work with, then we call them unpaired population. Unpaired means they have nothing in common. They can't be paired. They're unpaired, independent. So the samples from two populations are independent if the samples selected from one of the populations have no relation with the samples selected from the other population. For example, a group of male versus a group of female. They have nothing in common. They are two different species, so they are independent. On the other hand, if you're working with dependent samples, we call them paired samples. So the samples are dependent if each measurement in each sample is matched or paired with a particular measurement in the other sample. So if they are somehow related, then we call them dependent or paired sample. For example, pre-test versus post-test. We are taking the same test. One test is taken before we learn the lesson, and the same test we are taking after learning the lesson. So we have something in common, and that thing is test. In both scenarios, we are taking test. So pre-test versus post-test, if you're working with that scenario, that means you're working with dependent samples. Another way to consider this is how many measurements are taken of each subject. If only one measurement, then it's independent. If two measurements, then paired. For example, we are taking two measurements from the test. One is pre, one is post. So they are dependent of one another. On the other hand, if you're working with male versus female, they don't have, we are only working with one measurement, something like the height of male versus female or the weight of male versus female. So you're only working with one measurement. So the two groups you're working with, male and female, they're independent. So if you're working with one measurement, it's independent. And if you're taking two measurements or more than one measurement from the same two groups, then somehow they are dependent. Exceptions are in familial situations, such as in a study of spouses or twins. In such cases, the data is almost always treated as paired data. Now, if you have independent means, so you're working with mean, as with comparing to population proportions, when you compare to population means from independent populations, the interest is in the difference of the two means. What it means. Like before, we have two scenarios. Either you're working with proportion or you're working with mean. So when you work with proportion, we go in one direction, and when you work with mean, population mean, we go toward another direction. And when you go toward the mean direction, we want to see the difference of the mean, okay? In other words, if mu1 is the population mean from population 1, and if mu2 is the population mean from population 2, then we'd like to see the differences, which is mu1 minus mu2. So when we make a hypothesis, our hypothesis is based on the means, and we have two ways of comparing them. Either we look at the differences or we look at them individually. If mu1 minus mu2 is 0, in other words, mu1 and mu2 are same, then there is no difference between the two population parameters. Using the central limit theorem, even if the population is not normal, yet with a large sample, the sampling distribution is approximately normal. So if you're working with a large sample size and you don't know whether they follow a normal distribution or not, since it's a large sample, so by the central limit theorem, we automatically have normal distribution to work with. Why do we care? Because when you're working with normal distribution, our life is easier. So in this section or in this chapter, we have the main three topics. One is we are going to compare two means from two independent population or samples drawn from two independent population. This is scenario one. Another scenario, we are going to compare two means from two dependent samples or samples drawn from two dependent populations. So in both cases, we are working with mean. So for mean, two scenarios. Either we have independent or we have dependent samples to work with. And we have a third scenario. We are working with proportions. And when you work with proportions, we only work with independent sample. So for independent, we have either the mean to work with or we have proportion to work with. Good news, I'm not going to go over any proportion questioning from this section, from this chapter. I'm going to only go over these two topics because these two topics are the most useful ones in real life, I think. But actually, no. I am going to go over only these two because in our book, they talked about these two mainly. So, the first one, we are looking at two means that are drawn from two independent population. Now, in this case, we don't care about the size of the sample. Our N1, N2, these are the size of the samples we drawn from the population. They could be same or they may not be same. We don't care. It doesn't matter. Now, if mu1 is the population mean for population 1 and mu2 is the mean 2 for population 2, sigma square 1 is the variance for population 1 and sigma square 2 is the variance for population 2. X1 bar is a sample mean drawn from population mean 1 and X bar 2 is a sample mean 2 drawn from the population 2. Then, in order to do the hypothesis testing, we are going to use these cases. Our null hypothesis is always mu1 equals mu2, which is same as mu1 minus mu2 is 0. Why do you care about this format? Because when you write mu1 minus mu2 equals 0, you can see clearly that your hypothesized value is 0. On the other hand, in here, you don't see it clearly. Okay? So if you write mu1 equals mu2 in your null hypothesis and you're using you need to find the test statistic, that is DOT, doesn't matter. Then you need to know your hypothesis value. So you don't see it clearly here. So if you rewrite this equation as mu1 minus mu2 equals 0, Now it's clearly visible to you what is our hypothesis telling, but they are the same thing. So for null hypothesis, if you say that two population mean are equal, then alternative had three choices. Either they're not equal, like this one, or one of them, mu1 is bigger than mu2, or mu2 is bigger than mu1. So three scenarios for alternative hypothesis. Either they're not equal, or population 1 is bigger, or population 2 is bigger. So if you say they're not equal, you can rewrite this as same as mu1 minus mu2 is not equal 0. They are the same thing, same notation. If you say mu1 is bigger than mu2, this is same as you are saying mu1 minus mu2 is bigger than 0. Because if you subtract mu2 from both sides, you get the exact same thing. And if you are writing mu2 is bigger than mu1, then this is same as you are saying that mu1 minus mu2 is less than 0. So all three notations are same, but they're written in different ways. Now, when to use which test? This is a summary of this chapter. First, we have unpaired data. Unpaired data means the population you're working with, they're independent. Independent. So two populations are independent. Then you have two choices. Either you are testing the mean or you're testing the proportion. If you're testing the proportion, then you're going to use two sample proportion z-test. There's only one method, okay? Two sample proportion z-test, which we are not going to do in this class. And then if you are doing test on the mean, then you have two choices. Either you know the population standard deviation, or you don't know the population standard deviation. Standard deviation is square root of variance. So it doesn't matter which one you know. If you know one of them, you know the other one. So like before, if you know your population standard deviation, then you're going to use z-test. But if you don't know your population standard deviation, then you have two choices. Even though you don't know your population standard deviation, but somehow you know that the population standard deviation are equal. We don't know how much are they, but somehow we know that the two populations, they have the same standard deviation. If they're the same standard deviation, then we use equal variance two sample t-tests. But if the population standard deviation are not equal, then we use unequal variance two sample t-test. So based on the information you have, we use different testing. And you must remember all of this. So for independent population, we have a few branches to work with. For paired data, it means it's dependent. Dependent. If you have dependent population to work with, then you have only one choice. You must use paired sample t-test. Okay. So, any questions so far? Was anything I explained was confusing? I think. So let me erase all of these. If you want, you can take a screenshot here, or you can just use our lecture notes. Post it on Blackboard. Paired means we have dependent population. It means the two population you're working with, one depends on the other one. Unpaired means they have no connection. So we are working with two independent population, like male versus female. They are unpaired because they are independent of one another. Dependent, it means pre-test versus post-test. So they have a connection test. Now, depending on where you are standing, I put together their test statistic formula and how do you find confidence interval for each case. So this is too small. That's why I'm going to go over one by one. First, this one. If you have two independent population, in other words, the two samples you're working with, they're drawn from two independent population, and you know your population standard deviation, we are going to use two sample z-test. Now, for two sample z-test, the test statistic is this one. We subtract the mean for the sample, and we subtract the hypothesized value. This is hypothesized value. It means from the null hypothesis you get the value from the null hypothesis. And then we divide it by population 1 variance divided by the sample size 1. We add population 2 variance divided by sample size 2. Whatever we get, that's the test statistic for Z. Now the next one, if you're working with two independent samples, but you don't know the population variance. However, you do know that the two variants are equal. In that case, since we don't know the population standard deviation, so we need to use t-test. The formula to find the test statistic is this one. Now, this is a big formula. We have a SP square. That SP is this big formula. Okay, so this formula is kind of messy. However, good news is that to find the critical value, our degree of freedom is n1 plus n2 minus 2. It means you add the two sample size and you subtract 2 from the sum. So even though the test statistic is messy, however, degree of freedom is easy. And we call it pooled sample. I'll explain later what is pooled mean. And then to find the confidence interval, we use this formula. There's nothing to explain this formula, okay? We just have to remember them. So, if you know that the population variances are equal, then we use the messy formula to find the test statistic. However, if you know somehow that the population variance are not equal, so population 1 sigma square 1 is not equal sigma square 2. We don't know what is sigma, okay? We don't know that. But somehow we know that the variances are not equal. If they're not equal, then we use this formula to find the test statistic. Good news, this is easy to compute. Bad news, to find the critical value, the degree of freedom we need to use is a messy one. Okay. So from this degree of freedom, we don't get a whole number, we get a decimal number. Since we get a decimal number, so we always have to round down to get the whole number. For example, if you have 12.7, it's not 13, it's 12. Or if you get 12.1, this is 12. Or if you have 12.5, it doesn't matter what do you have after the decimal. We always round down to be safe. Okay? Because degree of freedom means 1 unit less than number of people for other cases. So it has to be integer. So since you're working with people, we cannot have a decimal people. So you always round down to have a whole number of people. Thus you always round down for degree of freedom. So this formula has a easy test statistic formula and a messy degree of freedom formula. And this is what we use to find confidence interval. Now the last scenario, if you're working with two dependent samples, it means one sample is somehow related to other sample. Then we use paired two-sample t-test. And in this test, our life is even easier. We look at the differences. For example, let's say you have pre-test versus post-test, and you have a bunch of data for that. So in that case, we don't work with individual data. Instead, we take the differences. So differences could be post-test minus pre-test. And with the differences, we find what's the mean of the differences, what's the standard deviation of the differences, and we apply that to get our test statistic. And in here, our degree of freedom is easy. It's 1 unit less than your sample size. And this is the confidence interval formula. So I gave you all the information you need to know to do any question from chapter 11. So make sure you have this written down on your cheat sheet as clearly with as details as possible. As much details as possible. Now you're going to do the testing. When you do the z-test, it means you know your population standard deviation or variance. So how do you do hypothesis test? Just like before, our step 1 is stating the hypothesis. So null hypothesis is always equal. The two means are equal, or the differences is 0. Yeah. For alternative, we have 3 choices. They're not equal, means the differences is not 0. Or population 1 is bigger, it means the difference is positive. Or population 2 is bigger, it means the difference is negative. So 3 options for alternative, only 1 option for null. Then we go find the test statistic. Since we know population standard deviation, so we're going to use Z, and that's the formula. Once you know your Z, we go find the critical value from table. And then you compare them. Same rule apply. If the test statistic, the positive sign of the test statistic is bigger than critical, then we reject null. Otherwise, we fail to reject the null. Once you do your hypothesis test, at the end, you do your conclusion. Okay. Now, when you don't know population standard deviation, then we use t-tests. And t-test can be used if we have samples are normally distributed, or we have a large data set. Now, here comes the word pooled variance. So even though we don't know the population variances, but we use a version of the t-test that combines or pools. So pools means the combination, we combine the variances. Okay, the sample variances we are working with, we combine them to estimate a single shared variance for both groups. So we assume the original variances are equal, the population variances, even though we don't know them, we assume they're equal. This assumption can help increase the test statistical power, but it requires us to assume the population variances are equal, even though we don't know exactly how much is that. To make this assumption, we often perform a preliminary test for equality of variances. We are not going to learn this in this class, but one of them is Levin's test or the F test. With those, we can have some idea about population variances, whether they're equal or not equal. And if they're equal, blah, 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 blah. I already explained everything. It's a messy formula, but unfortunately, we need to use this. And then if they're not equal, the population variances, then we use Walsh test. And this version of the test does not pool variances. That's why we call them unpooled. It means we don't combine the two sample variances. Instead, it accounts for each sample's variance separately, making it more robust when population variances are likely unequal. This approach is often the default when we have no strong reason to assume equal variances or when our preliminary test suggests significant difference in sample variances. In other words, if the sample variances are not equal, we use this, or if you don't know whether they're equal or not, using this one is safer. So it has a simpler test statistic, but it has a messy degree of freedom. So this degree of freedom we use to find the critical value. We need to use that formula. And then we follow the same procedure. We state our hypothesis, compute the test statistic, either using the simple one or messy one, and then we find the critical value, either using simple degree of freedom formula or messy formula, and we use one tail or two tail. So let me refresh your memory. One tail means our alternative has a bigger than or less than sign. So I should have 8 show. So alternative has bigger than or less than sign. We use one tail, and we use two tail if our null if our alternative hypothesis has not equal sign. Not equal sign means two tail, and other inequality means one tail. And then we follow the same procedure, like same rule like before. If the test statistic is bigger than critical, we reject. Otherwise, we fail to reject. And then state our conclusion. And population variance equal or not. If you don't know, then the Walsh method is safer to use because it helps us to avoid type 1 error. It means we reject the null when it's actually true. Any question? Comments? Concern? Complaints? Thoughts? Anything? They're confusing. So you have to sit down quietly and gather all the information or write down all the information in your paper very carefully. I think this one is very helpful because here I told direction for each scenario. So we have so many directions to work with. See? So many paths we can pick, and from here we keep going this way. From here, this is the next step. From here, this is the next step. From here, this is the next step. So if you write down all of these like the way I did here, it will be easier. No problem. Now let's do some examples. Fun examples with these. The National Sleep Foundation surveyed representative samples of adults in 6 different countries to ask questions about sleeping habits. Each person in a representative sample of 250 adults in each of these countries was asked how much sleep they get on a typical work night. So, 6 countries, each country has 250 adults. I don't know how did they ask all these people. So basically we have 6 times 250 people. And individually to each of them, they asked, how many hours do you sleep on what night? Now, United States, the 250 people from United States said they typically sleep 391 minutes with a standard deviation of 27 minutes. Now, 391 minutes, let me make a guess. I mean, not guess, let me see how many hours. 399 minutes divided by 60 minutes. Around 6.5. So people in the United States, they usually sleep 6.5 hours per work night, which is standard deviation of 27. But people in Mexico, they said they sleep on average 426 minutes, which is standard deviation of 42. So let me also check how much is this. 426 divided by 60. Wow. They sleep around 7 hours per night. Oh, half an hour more. Not bad. So, we want to see. The report concludes that on average, adults in US get less sleep on work night than adults in Mexico. So by observing these 6 times 250 adults, or not by observing, by getting their surveys, the report concluded that, well, people in US sleep less than people in Mexico. Now, our job is to figure out whether their conclusion is reasonable or not. It means, do we have enough evidence to conclude to agree with this conclusion based on the samples we worked with. That is our job. And we want to do it using 95% confidence. So with 95% confidence, do we have enough evidence to conclude that US people sleep less than Mexican people on weeknights based on the samples we worked with? So did you guys understand the scenario, what we are working with here? Any question about the scenario? Is anybody confused? No. So once we make this, once we verify this, whether it's true or not, then they're asking us to construct a 95% confidence interval to estimate the difference in the mean amount of sleep on work night for adults in both countries. Like, what's the difference between the two countries, the mean difference between two countries' sleep time? We want to construct that with 95% confidence. Now, nowhere it mentioned about variances, population variances. So we have no idea whether we are working with equal variances or unequal variances. Since we don't know, so it's up to us. You choose which method you want to pick, okay? So I did this before with equal variance. I'm assuming they have equal variance because I think it's because we have the same amount of people from each group. So probably they have the same variance. Probably. Who knows? So A, we are doing hypothesis testing. So we assume, let's say, mu A is mean sleep time for Americans, and mu Mexico, mu M is the mean sleep time for Mexican. Then we can make a null hypothesis that mu American equals mu Mexican. It means their sleep time are same. By default, we already assume they're same. If we do that, this is same as we are saying that the mu American minus mu Mexican has no differences. The differences is 0. And I'm writing this way because in the formula, we need to find out, we need to substitute how much is this. So this is equal. This is equal 0. Our alternative hypothesis, we have mu American versus mu Mexican. Tell me, what would be your alternative hypothesis? Not equal, bigger than, or less than? Which one? We get the alternative hypothesis from the claim. What is the claim here? Less. Good. Adults in US get less sleep than Mexican. So Mexican gets more sleep than Americans. That is our claim. Now, since this is our claim, so it's one-sided, one tail alpha, and our alpha is 0.05. Now for degree of freedom, degree of freedom is n1 plus n2 minus 2. I'm going to use easier degree of freedom. So we have 250 plus 250 minus 2. 25 is 500. 500 minus 2 is 498. So 498 degree of freedom with 1 till alpha 0.05. We can actually find our critical value here. T critical. We need to go to our T table. Oh, I didn't ask you. Why you are using T? Why you are not using Z? Is anybody confused about that? Why you are using T, not Z? So we have degree of freedom 498. Yes, we are given sample standard deviation. See here, they gave us sample standard deviation. These are S, not sigma. So S are given, sigma not given. Since sigma not given, we cannot use Z because Z requires population standard deviation sigma. So we are using T, and our degree of freedom is 498 with 1 tail alpha 0.05. So look at here, 1 tail alpha 0.05. 1 tail alpha 0.05 is here in this column. Unfortunately, we don't have 498 in our degree of freedom. We have 60, 80, 100, and then suddenly 1000. So, which one are you going to use for degree of freedom? What do you think? Any idea? We don't have 498 in the table. So which degree of freedom are we supposed to use? Repeat the number again. Look at the degree of freedom on the table. So the first column is degree of freedom. We have 1, 2, 3, 4, 5, 6, 7 till 30, and then 40, 60, 80, 100, 1000. But we need degree of freedom 498. We don't have 498 in our T table. So which degree of freedom we're supposed to use? Good job, Miyako, 100. When we don't have the degree of freedom given to us, we go to the take closest degree of freedom. So 498 is closer to 100 than 1000. So we are going to take 100 degree of freedom with alpha 1 tail 0.05. Alpha 1 tail 0.05, that's the number we have, 1.66. Yep, Queenie, good job. So this is 1.66. We found the T critical easily. But finding the test statistic is harder here. So we have to take our time. The formula says T statistic. The formula from before, it was x1 bar minus x2 bar. We are subtracting hypothesized value, which is mu1 minus mu2. We are dividing everything by SP square, which is multiplied by 1 over n1 plus 1 over n2. And then do the square root of everything. And then they have a formula for SP square. Let me write it here. SP square is n1 minus 1 times standard deviation 1 square plus n2 minus 1 times by standard deviation 2 square we divide everything by n1 plus n2 minus 2. That's why I hate this formula, because this is too much. So you have to do it step by step. n1 minus 1. Our n1 is 250. Yep. Our n1 was 250. N2 was 250. Okay. This is given to us. N1 minus 1 means 249. We are multiplying by S1 square. So from here, our S1 is 27 and our S2 is 42. So let's write this down here so that I don't forget. Oh no. Oh, I have to move forward. Okay. Finally back. It is my test statistic T value. I hate it. So the T was what, 1.66. And 1 is 250. Let me write it here. Let me change the color. So this is given to us. N1 is 250, N2 is 250. S1 was 27, and S2 was, I forgot, 42. So this is given to us. Given. So S1 is 27. So this will be 27 square. Plus N2 minus 1, which is 249. And we are multiplying by S2, which is 42 square. And then we are dividing everything by N1 plus N2 minus 2, which is 498. So 498. Since we don't have much time, let me do the calculation. It's 1, 2, what's wrong with this? 1246.5. You can verify this in case if I'm wrong. Now that number will come here. Let's change the color. This T square. SP means standard deviation for the pooled samples. Okay, now x1 bar minus x2 bar. Where I hit that? X1 is 391 and x2 is 426. So 391 for 26, 391 for 26, 391 minus 426, and we are subtracting this, which is 0. We are dividing by square root of 1246.5, and then we have 1 over n1 is 250, another n2 is also 250. It's a good practice to do, so you guys should try doing this calculation. If I'm not wrong, then it should be 11.08. So we have test critical compare with test statistic. We found our statistic is bigger because critical is only 1.66. Since statistic is bigger, so we realize that we reject the null hypothesis. Means we assumed that the mean sleeping time for American and Mexican was same. We reject that idea. Since we are rejecting this idea, so the conclusion we come up with is that at 0.05 alpha level, so at alpha 0.05, we have enough evidence to support the claim is that Mexican sleeping time is bigger than mean American sleeping time, which is the claim, the alternative hypothesis. So you're doing the exact same thing what we did in chapter 10. The only difference here is that our calculation is heavy. And here I have written down all the details. Conclusion, yeah. And I'm too lazy to do the confidence interval. So let me just show you the confidence interval. So confidence interval, you can use 1.96 for Z since you have a large number, or we can simply use what did we get for the critical 66? Or you can use 1.66. So in the book, they are telling us that oil 250 plus 250 minus 2, 498 is a big sample to work with. In other words, 500 people is a big sample to work with. So since it's a big sample, we don't have to use the T critical value. We can simply use Z critical value because they become normal anyway for being a large data set. So either you can use the Z critical value or you can use T critical value. If you observe, they are very close to one another. And then you just substitute all of these in this formula, whatever number you get. I forgot to interpret the confidence interval. So this confidence interval is telling us that the mean sleeping time difference from Mexican to American is around 28 minutes to 41 minutes. So Mexican people sleep around 48 minutes to 41 minutes more than American people on week work night. Okay. Any question? Any question, comments, concern, complaint, anything? Nothing.
There's just like a lot to remember.
And the calculation is very easy to make mistake. So when you do all these calculations, you have to be very careful. Let me go over one more example, which I'm too lazy to do. So I'm just gonna show you the result. When after class, probably 1 hour later. Okay, Yusuf, no problem. You can ask all these questions, next class in person. So yeah, a good way of practicing all these materials we learned today is by doing the homework. So do the homework and try to do them honestly because you have to take an exam on this. Okay, the next question, an interesting one. A psychologist was interested in exploring whether or not male and female college students have different driving behaviors. The particular statistical question was as follows. Is the mean fastest speed driven by male college students different than the mean fastest speed driven by female college students? She conducted a survey of a random 34 male and 29 female college students. And this is the summary she came up with. Is there sufficient evidence at the alpha level 0.05 that her claim is true? Now we're assuming the population variances are not equal. Since they are telling us this, that assume that the population variances are not equal, that means we go to the branch which I showed you before. Here. Let me erase all of this. So you are working with population mean. So population variance is unknown and we have unequal variances. So it's the third branch, which is this one. So when population variances are unequal, our test statistic is easy to find, but degree of freedom is a mess. Okay. So we go there and do our hypothesis testing. Before finding all those test statistic or critical value, first we have to come up with the what is called hypothesis. So null hypothesis versus alternative hypothesis. And since you're working with male and female, let's say mu m is the mean of male and mu f is the mean of female. So mu m versus mu f. Now, based on the claim, what should be our alternative hypothesis? How we are comparing the mean male versus mean female. Any idea? Is the mean male different than mean female? How are you going to express this using mathematical notation? Come on, guys, we don't have much time. I'm asking you not a hard question. I'm asking a very easy question. Rewrite this sentence using mathematical notation. How are you going to express this sentence?
I will use like either greater than or equal to or less than or equal to.
But did they mention greater or less? They are
No,
telling us
there's a
different.
difference.
So how can you express different using which notation? Not equal, bigger than, or less than? One of them.
Less than.
Why?
Oh
Did
no,
they
wait.
say it's less than? The other one?
No. So I guess then they're not equal to.
Exactly. See, the last one, they specifically mentioned less than. So we use less than sign. But here, they did not mention less than. They did not mention greater than. They're mentioning it's different. Different means not equal. So alternative hypothesis has not equal sign. So what is our null hypothesis? What does null hypothesis have? Which sign? Null hypothesis always have equal sign. Good job, Salma. Null hypothesis always have equal sign in this class, and alternative has three choices. The first one we had less than, for this one we have not equal. So from this one we get our hypothesis value. Mu male minus mu female gives us 0. We are going to use this 0 for our test statistic, in our test statistic for this quantity. So what else? I'm too lazy to do everything. So let me just go over the solution. We have significance level alpha is 0.05. So alpha is 0.05. Since we have not equal sign in our alternative, so we are working with 2 till alpha. Now 2 till alpha, degree of freedom is harder one. So let me go over the degree of freedom now. This is the formula for the degree of freedom. Some people use this V1 and V2. They're saying that this is V1 and this is V2. And then you're simply substituting all those numbers in this formula. So it doesn't matter which one you use, you're going to get the same result. So to find degree of freedom, you need standard deviation 1 square over sample size 1 plus standard deviation 2 square over sample size 2. Whatever you have, you square the quantity. Then individual square, and you divide them individually by 1 and it's less than each sample size. So you're going to substitute everything here, and you're going to get the degree of freedom 55.5. But like I said before, the degree of freedom always should be round down. So it's not 56, it should be 55. Now 55 degree of freedom with 2 till alpha 0.05. If you go to the table, 2 till alpha 0.5 is here. So let me actually the other things. So 2 till alpha 0.05 is here. Degree of freedom is 55. We don't have 55. We have 40 and 60. So 55 is closer to 60. So our degree of freedom is 2. So we have 2 till alpha 0.05 with degree of freedom 55. T critical value is 2. Now we find the test statistic. This is the formula for the test statistic. They gave us x1 bar, x2 bar, and from the hypothesis, we know this is 0. And then they want us to divide sample variance 1 square by sample size 1, sample variance 2 square by sample size 2, take the square root, and then you get the number 3.54. So test statistic is 3.5, T critical value is 2. Since statistic is bigger, so we reject the null hypothesis. Null hypothesis says the male and female driving has no difference. Mean driving has no difference. On the other hand, alternative, we are claiming that they have some differences between them. So since we reject the null, so we have enough evidence at this alpha level to believe that the two mean driving speed are different from one another. We don't know how they're different. Is male bigger than female, or is female bigger than male? We don't know that yet, but we only know that they're different. Somehow they're different. They're not equal. And here in the homework, they also mentioned something like, at any rate, our conclusion would be the same regardless of whether or not we assume equality of population variance. So it means, see here, they're specifically telling us that assume we don't have equal variances. Well, in reality, it doesn't matter. It doesn't matter which formula you use. At the end, you'll get the same result anyway. So I don't know why we had two different formulas. So I read about it, and it says this the information we get using this method, like using unequal variance, gives us more accurate results than using assuming equal variances. And that's all about working with two independent population, whether we have equal variance or not equal variance, and whether we know the standard deviation, population standard deviation, or we don't know population standard deviation. So I went over 3 cases today. When you don't know population standard deviation, we use T. For T, there are two scenarios. Either they have equal variance or not equal variance. In reality, it doesn't matter. You can use any one of them. And if you know your population standard deviation, your life is easy. You simply go to Z and get the Z value from the table and the test statistic. In our next class, we are going to work with two dependent population. And then we'll be done in chapter 11. And we're going to go chapter 12. So I believe there will be one day we're not going to meet. So let me tell you why we're not going to meet. Let me make it bigger. So today is 13. So we are done with this class. Then we have a class on Monday, another class next week, Wednesday. Then we have our exam on 24. And after the exam, we're not going to meet because that Wednesday is a Friday schedule. So we have 2 more classes. In our next class, we're going to be completing chapter 11 and going to go chapter 12. And on 20, after we finish chapter 12, we're going to do a review if you have time. If you don't have time, then I'm going to just send you the review link from my previous semester. From my summer. I actually taught this class in summer. Okay. Any question before you leave? Any question, comments, concern? Anything? Heart rate problem from chapter 10? Okay, no problem. How difficult the exam question will be? I already posted the review sheet. So exam will have very similar question. Just the scenarios will be different. So your job is to figure out what is given in every scenario. So from chapter 9, these are the types of questions you expect to see. From chapter 10, we have many questions. You need to know what is given, and based on that, which formula you're supposed to use. Similarly, in chapter 11, we have only 2 types of question. One type is the two questions we went over today, and another type is something with dependent population. And then from chapter 12, we have 2 types. One is harder one, like question 3 is harder one. So I'm not going to put question 3 in this exam. Probably will see it in the final exam. So from chapter 12, I'm going to ask one of these, either 1 or 2. Okay. The exam will be hard if you don't know how to figure out what is given and which formula to use. Then you're lost. but doing many questions, doing lots of practices, it will be easier for you to see them. If you can see what is given and what formula to use, then this exam will be a piece of cake for you. So it's up to you how the test will be, how difficult you expect it to be. Okay, so goodbye, everyone. See you all again on Monday.
Have a good night.
You too. Heart rate, heart rate. Yusuf, what question you have about the heart rate problem? This is making money. Heart rate. This is IQ. This is test score. This is wasting time. This is protein diet for chirping. Okay. This question, right, Yusuf?
Yeah, it's that one.
So what question you have?
Okay, just like starting it off, like from like based on like the previous ones you did, like you could kind of see how it's easy to form your hypothesis and like the actual. For this one, like I'm just having a little trouble. Like first of all, like for forming the hypothesis, which is why I can really even start it when I tried. For
So if
essentially,
you read it, they give us many extra information. That's why it's harder to see. But
yeah,
let's read it carefully. It says this paper describes an interesting investigation of the possible cardiovascular benefits of active video games. Now, mean heart rate for healthy boys aged 10 to 13. After walking 2.6 kilometers per hour for 6 minutes is 98 beats per minute. So it did not mention about any sample. It's only saying mean heart rate for healthy boys aged 10 to 13. So this age group, do you think they are telling us about the population or sample?
population
Good. So that means the mean population for this age group is 98 beats.
98. Yeah,
So mean population is 98. Now they're walking 2.6 kilometers after 6 minutes. These are extra information because we look at mean to create our hypothesis, right? Our hypothesis is only based on mean or proportion. So here they're talking about mean. So we ignore all the other information. We only look at what mean we have for the population.
yeah, got it. That part kind of threw me off. And hold on.
Next, it's saying that we have 14 boys. So they're telling us our N is 14. Now for these 14 boys, heart rate was measured after 15 minutes of playing Wii bowling. The resulting sample mean. So sample mean means X bar. The sample mean is 101 and sample standard deviation, which is S, is 15. So they're telling us that we have sample mean and standard deviation. So just by knowing this, which test statistic we have to use, Z or T?
Would it be Z since they give you it?
For Z, what do you need?
Sample standard deviation.
Look at the Z. Z, 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 Z. Here. Z needs what? What is sigma?
Uh, Is the standard? Sorry, I just got called for something. Sorry, I don't remember.
You don't remember sigma? Do you want me to punch you? Sigma is population standard deviation. Now look at Z versus T. It's exact same formula. The only difference is Z has a sigma and T has an S. What is S? S means what?
Sorry, can you? Yeah.
What the symbol S represents? It's the sample standard deviation. So I see your main problem. Your main problem is you don't know your variables yet. So you should write all of this down. Mu means population mean. Sigma means population standard deviation. X bar means sample mean, MEAN, and S means sample standard deviation. P means population proportion. P hat means sample proportion. Okay, so you must know all these symbols. The population symbols, we call them parameter. For the symbols for sample, we call them statistic. Now, in our example, they gave us, they gave us sample mean with standard deviation. So they did not mention the standard deviation is derived from the population. For population, they will tell you that population standard deviation is this. If they don't tell you that, but the standard deviation is next to the sample mean, so you have to assume that the standard deviation is derived from the sample. So this is S, not sigma. Since S is given, not sigma, so we cannot use Z. We have to use T statistic. Because T statistic has the T as a sample standard deviation. Why do we care? Because when you use T statistic, you need to find T critical value. If you use Z, then you need to use Z critical value. That's why it matters which test you are using. In here, Z doesn't make sense. First of all, our sample size is very small, 14. And second of all, we don't have population standard deviation. So T makes sense here. We use test statistic for T. We compare that with the critical value for T. Okay, now the next sentence is, for purposes of this exercise, assume that it is reasonable to regard the sample of boys as representative of the boys. So they are telling us that all the conditions we're supposed to check in real life to conduct a t-test is satisfied here. We have a population representative sample and our distribution is normally distributed. Now they're asking, does the sample provide convincing evidence that the mean heart rate after 15 minutes of doing blah 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 is different from the mean heart rate after doing 6 minutes of walking on treadmill? So here all the other informations are kind of confusing, but I highlighted or bolded. I bolded the word different. So different, the word different, gonna decide your alternative hypothesis. So remember, the null and alternative, they're based on population. So you see that we are comparing mean heart rate of two things. So mean heart rate of the boys, they told us it's 98. So we believe that null hypothesis is mean heart rate for these boys after 6 minutes is 98. On the other hand, our alternative claim is that what?
That's is it just simply just telling us it's different? Is that what the different is
So
telling
which
us?
symbol you're going to use? For alternative, you have three choices. Not equal, bigger, or less. Which one makes sense here?
Would it be less?
What does different mean? Did it tell you that
That's,
we have a less heart rate? Did they mention that?
no, so would it be the not equal sign if it's just not 98?
Exactly. Different means we don't know. Is it bigger or less? So it's not equals 98. Okay? Is it clear now?
Yeah, I think I can go off from this. Thanks.
So I gave you all the information which was given in here. Also, I believe I have the solution here. So if you want to check after doing by yourself, you can check your solution in this one.
Definitely appreciate it, Professor. All right, that'll be all. Okay, see you next week. Thank you.
That's it. Okay, have a good night.
Thank you, Professor. Have a good night.
You too. Bye, Tao.
Bye. Thank you for the question. It was really helpful.
No problem.
Yeah, have a good night. Bye.
Bye.